Let's talk about 12.1 scatter plots and correlations. Now, with this, hopefully you guys remember how to make scatter plots, but now we're going to learn how to kind of interpret them as well as, calculate and interpret the correlation relationship between two variables. Now, a scatter plot itself is basically a graph on the coordinate plane system that contains a point um, for a pair of data. So you've got two axes, an x-axis and a y-axis. The x-axis being a horizontal represents one variable, and the vertical being the y-axis represents the other. Please understand that this is not a line graph, okay? This does not mean the points are all connected with dots. This is, however, the points are just put on the graph, hence the reason why it's called a scatter plot. They're just kind of plotted all over there. Now, with your scatter plot, please understand that there is a choice of which variable to put on which axis, and it depends on what we believe as one variable might influence the other. If the type of relationship exists, we can say that the change in one variable that's going to be the explanatory variable, influences the change in the other variable, and that other variable is going to be the response variable. So one is going to explain the response in the other. We've used these types of words before. We called them independent and dependent, so this is not a new thing. And again, independent would be our explanatory variable. Our dependent is going to be the one that has the response to it, hence normally why we let y be our dependent. It's important to note on a scatter plot that allows us to kind of identify types of trends that happen. For example, do all these points fall in maybe a linear pattern? Or maybe they fall in a bit of a curve pattern? Or maybe there's just no pattern at all. Now, if the points do have a linear shape, and that's what we're going to focus on right now, is if they have a linear shape, how close to a straight line are they? Is that pattern in a positive slope, meaning that it looks like it rises from left to right? Or is it in a negative slope, meaning that it falls from left to right? And you'll notice I do say fall from left to right or rise from left to right. Again, we always read a graph from left to right. So I'm going to use this type of data for a couple of problems. So when I refer back to 12.2 table, this is basically a sample of NFL quarterbacks in the 2011-2012 season, and we're looking at the number of passing touchdowns, their 2012 base salary, now that is in millions of dollars, and what was their quarterback rating. Okay, and again, this is for a bunch of different actual real life people, and there are the sources there if you would like to take a peek at the sources. So we're going to start off by using the data from that 12.2 to produce a scatter plot that shows the relationship between the base salary of an NFL quarterback and the number of touchdowns the quarterback has thrown in one season. Now, the first thing that we're going to do when we do this type of thing is we might actually expect to see the number of touchdowns a quarterback throws in one season to influence their salary. Now, taking that into consideration, that means we're going to place the number of touchdowns on the x-axis, and we're going to put the salary on the y-axis. Now, in your calculator to do this, what we're going to do is you're going to start by hitting Stat and Edit. So I've already gone ahead and placed all this in there. And again, what we're doing is we're creating the scatter plot. We're just going to do the scatter plot itself. And the reason why we want to do the scatter plot is we want to kind of look at it and see, is there a bit of a relationship or not? Okay, so I've got all my data in there. List 1 being our touchdowns thrown, so the passing touchdowns, and list 2 being the salary in millions of dollars. So stat, edit, put all this in, so this is not new to us. But then I'm going to hit second y equals, and this is going to go to my stat plot. Now I'm going to turn it on, so I'm going to hit enter, make sure that on is highlighted, and I am also going to make sure that the little dot 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 symbol is selected here, and list 1 and list 2 is selected. Again, if you have a color, you can choose any color you want. I do recommend the big kind of like square looking dots. Makes it a little bit easier for them to stand out, but you can do smaller if you feel like it. Okay, once you've got that in there, I am going to go to y equals, make sure this is clear, and then zoom 9. And again, I always want to hit zoom and the number 9. And again, just for, I know I did that quick, zoom. The number 9 says stat, and what that does is that, again, takes that calculator and recalculates it for what's in that list. And our graph looks something like this. Now, as I take a peek at that, that doesn't look very, I don't know, it doesn't look like it's all like around a line or anything. So here's a little bit better, bigger idea here. Made it look a little bit nicer and labeling all the sides. Again, in your calculator, you don't have the option to label the sides, but as we write it down, we can. And as I look at this scatter plot, one of the things I begin to notice is there's really no pattern that's evident here. What that tells me is that basically, since there is no pattern, there's probably indicates that the two variables do not really have much of a relationship. Okay, well, let's try this again, and let's do a scatter plot showing the relationship between the number of touchdowns thrown in one season and the corresponding quarterback rating for the given sample of NFL quarterbacks. So again, we do kind of expect, sorry, I went through that a little quick. We do kind of expect that the number of touchdowns thrown is going to influence the quarterback's rating this time. And so that's just going to be one of many things. So as I look at this, when we run these, again, I would say stat, edit, put it in the calculator, and then run these all together. And it would look something like this as we take a peek at it. Do notice one of the things here, it does look like my number of passing touchdowns as I move from left to right here, that these kind of cluster together with what my quarterback rating is. And it does kind of look, as we notice, it is going up from left to right, so it does look like it has kind of a positive correlation. And it's not a perfectly straight line, but it does look like it's kind of all gathered around kind of possibly a straight line there. So that's one of the things we want to notice. And because of that, I want to go into a little bit more depth of what we mean by this linear pattern and this positive slope. So a linear relationship requires two variables. So two variables have a linear relationship in a scatter plot if they follow roughly a straight line. It doesn't have to be perfect, but roughly they gather around a bit of a linear area. Now, when the points in a scatter plot do roughly follow a straight line, the direction of the pattern can tell us whether something is positive or negative. A positive slope indicates that one variable increases, so the other values also increase. And this type of a relationship between those two variables is considered a positive linear relationship. Now, a negative slope is going to indicate the values of one variable increasing while the other one decreases. And that type of relationship will be called a negative linear relationship. And again, positive, again, we read left to right. So left to right, it looks like it goes up, and left to right, it looks like it goes down. So negative slope here, positive slope here. And again, I'm not talking about anything being perfectly in a straight line, but just kind of looks like they gather around a bit of a line. So let's just take a peek at some possible points in a scatter plot from two different variables, and let's see whether or not they would have a positive or a negative slope, or maybe they may not even follow a straight line pattern. Maybe we can't tell. So our first example here is the number of hours you study for an exam and the score you make on the exam. Our second example is the price of a used car and the number of miles on that odometer. C is going to be the pressure on the gas pedal and the speed of the car. And D is going to be the shoe size and the IQ for a person. We'll start with A. So if we think about it, the number of hours you study for an exam, as that increases, the score you receive on that exam is normally higher. So I would say that those actually have a positive slope, because the more you study, the higher you should get on your exam. Now, for the car, the number of miles on the odometer, as that odometer, meaning the miles that you've driven in the car already, as it goes up, normally the price of the car actually decreases. So I would say this one has a negative slope. Our third example was talking about the pressure on the gas pedal. So basically, pressure on a gas pedal would be the more you push on the gas pedal, well, then the faster the car's going to go. So I would also say those would be a positive slope as well. Our last example was dealing with shoe sizes versus the IQ of somebody. Now, common sense suggests that there's actually no relationship between the two, linear or even otherwise. There's been no data that shows that a person's IQ or intelligence quotient and his or her shoe size are related, so I would say there's no relationship between them. Now, when talking about scatter plots and their correlations, they can have what we call a strong linear correlation, meaning it's kind of really all tightly clustered around that straight line that we were talking about. It could have a weak linear relationship, meaning again, it still looks like it kind of looks like they pattern themselves in a straight upward line area, but it's a little bit more scattered. We could have something where it's not even linear in the relationship at all. So this doesn't look like a straight line. This just kind of looks like all these dots in one area. But we can also have what we call a non-linear relationship, meaning that it doesn't look like a straight line, but maybe more of a curve somehow. Now, in this section, in this class, we're not going to focus on the nonlinear relationships. We're just going to do the linears itself. Now, when talking about a linear relationship, we do need to talk about the Pearson coefficient. Now, the Pearson coefficient is the parameter that measures the strength of a linear relationship between two quantities of variables. Now, the correlation coefficient for a sample, and again, notice this kind of symbol here. It's not necessarily a P straight away, but a P that's for Pearson. This will be if I'm talking about it in terms of a population. If I'm talking about in terms of a sample, we use the letter R to denote that. And it always takes on the values between -1 and 1. And it's inclusive, meaning it can actually equal those 1s and -1. Now, if R is positive, that means the scatter plot has a positive slope. Okay. And if R is negative, that means our scatter plot has a negative slope. And again, we are referring only to the linears right now. If R equals 0, that means that there's really no linear relationship between these. If R equals 1, though, however, the data there means that it falls in a perfectly straight line. And normally we can find that data. This is very, very rare. If in the real world you get R equals 1, you probably did something wrong. Now, in math class, could it possibly happen? Well, yeah, because of some of the data we create, we've created it in a math class to make it work in a certain way. Whereas in real life, it's very rare to get it to equal R equals 1 or R equals -1. R equals 1 means it perfectly fits a straight line. Every single point is going to fall on the straight line exactly. R equals -1, again, every point fits perfectly on that straight line. Positive means it's positive 1 means it's a positive slope. -1 means it's a negative slope. Now, if the two variables have a strong positive or negative relationship, we do say that those two variables are correlated. So they have some types of correlation there. Do understand that the strength of that correlation is expressed by the absolute value of R. And the larger that absolute value of R actually is, the stronger the correlation. So again, if I'm closer to the end here, where I'm talking to R equals -1 or R equals +1, either end of it is going to be a strong correlation. Now, if I'm somewhere in the middle here, if I land perfectly at R equals 0, it means there's no linear relationship whatsoever. Okay. Now, how to find the Pearson correlation coefficient? Please understand that this is a really weird formula, and I do not expect you to actually memorize this formula whatsoever. But I do want to kind of show it to you. So for those of y'all that are in a lot of science classes, this is the actual formula, but a lot of statistical programs will actually spit this back out to you. So you don't have to go through all the work of how to do this by hand. So let's go back to the table 12.2 where we were talking about touchdowns that we threw for our NFL players and how much salary they got, their base salary. Now, when we graphed these, it was not looking like they had much of a relationship. So let's look at just that data, and again, this was the graph that we had, and we saw that they just kind of weren't really all together. Okay, so remember I said R is that really strange looking formula, and I do not expect you to actually do this by hand, so please don't. Please make sure you have your calculator with you. Okay, so in your calculator, what you're going to do is you're going to start by saying stat, edit, and type in these beautiful numbers. Okay, so I've got my calculator up. I've had stat, edit, I've typed in these beautiful numbers here that I see. And again, before you just double check on everything, make sure that you go back and double check that all these numbers do line up perfectly of what you have in the calculator. Okay, from here, what you're going to do is we're going to hit stat, we're going to arrow over to calculate, and you're going to go down to number 4, ln reg ax plus b. Okay, and then you're going to say list 1, list 2, and then we're going to say calculate. Now, some of y'all might have gotten this far and say, wait, yours shows an R and mine doesn't. Well, if yours doesn't show an R, we do need to make sure to tell the calculator to tell me the R. Okay, so for those of y'all that have a TI-84 Plus, just like mine here, I need you to hit the mode button, okay? And then you're going to scroll all the way down here to where it says Stat Diagnostic and make sure that on is highlighted. If on is not highlighted, it will not show that R, and we really need that R, okay? Now, for those of y'all that have this option when you hit mode and you cannot see the stat diagnostic, okay, again, you might have to arrow down to get to it. If you do not see it, then that means we're going to do it a different way. And so what you're going to do, for those of y'all that have the slightly different version of a calculator, like I say a TI-83, I want you to hit second 0, and then you're just going to scroll your way through this until you see stat diagnostic and turn it on. Okay. Now it is going to take you a little bit to get to it, so just be aware. Okay. It doesn't say stat diagnostic, it actually says diagnostic on, so just say diagnostic on, hit enter. It will bring you back to the home screen. You have to hit enter one more time, and then once you've seen it, it'll say the word done, and then you won't have to worry about this again. It will automatically work, okay? So stat, arrow over to calculate, number 4, and again, I'm going to make sure that it calculates here, and there we go. And now you should see the R's. If you don't, then please reach out to me and we will talk about that. Again, make note of this R right here, and again, write down as many decimal places as you need. So just in case you need to follow along with those steps, those are the steps. Now, from the scatter plot, again, remind yourself that when we were looking at them visually, we said that it didn't really have much of a correlation. And basically, the calculator confirmed that with its R that we saw. This R has a negative 0.251. So again, it says that it has basically a very weak negative relationship, if any exists. Now again, if we're going to do this one more time, so table 12.2, we're going to do the touchdowns versus the quarterback rating. So again, let's start by reproducing that data. So there is my numbers. Pause if you need to. And as we were looking at our nice, beautiful picture, we could see that as I looked at the scatter plot, it did look like they had something, like, it does look like they're kind of clustered together in a way, and it does look like they're kind of going in a positive version. So I expect my R to be a little bit higher this time, and I do also expect it to be closer to a positive 1. So in my own words here, I'm going to actually do all the steps again. So I'm going to hit stat, edit, type all the stuff in list 1 and list 2. And then I'm going to hit stat one more time, arrow over and choose calc, so the calculate menu, and then option number 4, ln reg ax plus b. Make sure that list 1 and list 2 is listed, and then hit enter and calculate. Now, from there, you should get this beautiful screen here. And as we look, we did expect that correlation coefficient R to be closer to 1, and this time we can see that it was actually a 0.925 approximately. So it is actually a heck of a lot closer to 1. So I'd say this one does have a very strong positive correlation coefficient. Now, let's talk about using critical values with that Pearson correlation coefficient. And we're going to determine whether the significance of a linear relationship. Now, determine the significance of a relationship, the level of significance we might have. Please understand we talked about these when we were looking at hypothesis testing. So we're actually going to look at some of the hypothesis testing in a moment. The term statistically significant for a Pearson correlation coefficient indicates that the significant linear relationship between the two variables there is high enough, and you are going to need to know your level of significance here. And remind yourself, we did talk about that level of significance being called A, or also known as alpha. We prefer to use the word alpha. So as long as the absolute value of R is greater than or equal to R alpha, we can say that it's statistically significant. Okay. Now there's a few different ways in which you can find these critical values. You can actually use it using your calculator, but I do also suggest just take a peek at table 1 to determine if the correlation relationship between them, what it exactly is. And we're going to use a significance level of 0.05 to determine whether or not is it significant or not. So the first thing you have to do is you have to find your critical value. So the critical value comes from the alpha, and it always comes from your alpha itself, which our case here is 0.05. And we also need to know what our n was, and n is again how many items were in the sample, and as we were looking at earlier, our sample had 10 quarterbacks, so n equals 10. And so I'm going to use table 1, and I'm going to find where does the row for n equals 10 intersect the column for alpha is 0.05. As we can see here in my beautiful table, we do notice that they do have that relationship between the two. Okay, and again, make sure that you're finding this and where alpha intersects. To see this table, you can either print it out yourself, or guys, just remember that if you hit the table option in your Hawks homework, that you'll be able to see this as well. And it's the one that's labeled the correlation coefficient. Okay, so now that we know what R alpha is, we have to compare that critical value to the correlation coefficient that you found. Now remember in the very first one we found that was 0.251. And again, this is what we did earlier, and we found that. And that came from the calculator. Okay, this R alpha is going to come from our table. And I do notice that 0.251 is smaller than 0.632. So therefore, that basically tells us that there's really no linear relationship between those that is statistically significant. So it's not statistically significant at a 0.05 level of significance, meaning that basically we don't have enough evidence at a 5% level of significance to conclude that this linear relationship even really exists between the number of passing touchdowns for the 2011-2012 season and the base salaries of our NFL quarterbacks in 2012. Now, I do want to remind you that we can determine whether or not this testing of this linear relationship, I can be testing it using those hypothesis tests that we were using back in chapter 10. Now with my hypothesis test, there's going to be the option for a two-tail test. And again, how do I determine if it's two-tail? Well, that's going to be that Pearson coefficient does not equal 0. That's going to be a two-tail. Okay. Now, the null hypothesis always contained the equal sign. So if I say that Pearson coefficient equaled 0, this means that there is no significant linear relationship. And if it's something other than 0 within the significance level that we're looking at, then that means that there is significant linear relationship. For a left-tail test, the same rules are going to apply. Again, looking at that alternative hypothesis that Pearson coefficient is less than 0, meaning that we are implying that there's a negative relationship. And for a right-tail test, again, looking at that alternative hypothesis, your Pearson coefficient is going to be greater than 0, meaning that we have a positive linear relationship. Now, the test statistic for determining whether or not this is significant or not actually uses the correlation coefficient and is given by the following formula: T equals R divided by the square root of the quantity of 1 minus R squared divided by n minus 2. Now, I am going to show you how to actually use this formula one time by hand. And again, if you use the tutor button in Hawks, they're going to show you how to do it by hand. However, there is a way to do this all with the calculator, and the calculator will split it back out for you. Okay. One of the things that you need to know when doing a hypothesis testing with linear relationship here, so we're using a hypothesis test for a correlation coefficient. First of all, anytime I'm referring to R, R is representing the sample's correlation coefficient. N is the number of data pairs in that sample. And the number of degrees of freedom for a t-distribution for a test statistic is actually now given by n minus 2. And again, this is for something that is a correlation coefficient. If it's just a regular one, we just use n minus 1 as our degrees of freedom. But because this is a correlation coefficient, it's n minus 2. Now, do remember that the rules for the rejection region for the testing for linear relationships, again, we reject if our t-value falls within the rejection zones. So these are the 3 items that you want to kind of make note of for the different rejection zones that we have. So let's test this out. And again, I'm going to show you guys how to do this by hand, and then we'll do it how to with the calculator. Okay, but again, I'm going to show one time with by hand. If you, again, are looking at your Hawks homework and clicking tutor every single time, it will show you how to do it by hand every single time, but there is a quicker way. So we're going to use a hypothesis test to determine if the linear relationship between the number of parking tickets and the student receives during a semester and his or her GPA during the same semester is statistically significant at a 0.05 level of significance. And we're going to refer to the data in the following table. So to start ourselves off, the first thing we should always do when talking about anything that talks about a hypothesis test is write out what the null and alternative hypotheses are. So in our case here, state the null and alternative hypothesis. Now again, we basically wanted to test the claim that the significant linear relationship exists between these two things. I made no reference to it's positive related or negative related, just saying that it does relate somehow. Okay, so that means, because again I gave no direction, that this is that Pearson coefficient does not equal 0 is going to be the alternative, and that's the one that I am researching there. Okay, now that we know that this was a two-tail test, I also need to make sure I know what type of test statistic and the level of significance I'm dealing with. Now, we will use a t-test statistic method here. And again, this we've done it from previous sections before, but I also want to remind you that realistically, anytime we talk about linear relationships, it's always a t-test because you're never given that population standard deviation, hence the reason why it's always going to be a t-test. They do give me my level of significance there, so my alpha was 0.05, so we can continue on with that. Step 3 is we're going to gather our information and calculate the necessary sample statistics. So the first thing we're going to need to do is actually gather out what R is itself. So the first thing that we're going to do is we are going to be able to, whether or not these are statistically significant, I really do need to figure out what R is itself. So again, stat, edit, type in the items, okay? Double check if you want to double peek at it. So second y equals, make sure your stat plot's on, and then zoom 9. As I take a look at all these dots here, it looks like there might be a bit of a correlation. I'm not 100% sure here, but it does look like they might have a bit of a correlation. Again, this was that nice, lovely how many tickets that they had versus their GPA. And so here's 0, here's looks like 2, 3, 5, what is that, 4, 6, 7, 8 maybe. I'm not 100% sure. These may not represent 1 every single time. So, but it looks like it's a little bit kind of like a bit of 1. So when I hit stat and arrow over to calculate and run number 4 here, and again, calculate it out, I get my R to equal a negative 0.586619. Now again, we do know that n equals 15. Again, you'll have to physically count those out if you're using LinReg here. And again, as I take a look at that graph, I can kind of see where it gets that negative shape from. Now the question is this significant enough? Okay, it's not close to 0, but it's not perfectly close to -1 either. So is it at a significance level that we can say that there is a bit of a relationship? Now to do this by hand, again, remember the first thing you want to do is you want to write down all of the decimals that you possibly can, okay? Preferably, please note that when I wrote R down, I did write it down to 6 decimal places. Do not round it to 3 decimal places here because we're taking it a step further. So to avoid any additional rounding error that could happen with the test statistic, you want to make sure to use as many decimals as possible. Okay, and then you're just going to plug it in the T formula there. And again, this is a very different T formula, so understand that the T changes based upon what type of data we're running. And this again is we're doing a hypothesis test for a correlation coefficient for a linear relationship. Now, as you type that all in there, I get that was approximately a negative 2.612. We will need to go figure out what our alpha is. Okay, so with that there, we can use the alpha, T alpha. Remember, it's going to be a two-tail test, so that's going to be T alpha divided by 2. So 0.05 divided by 2. And you can either use the T distribution table or appropriate technology. Again, do make note that the degrees of freedom here are a little bit different than the n-1 that we've been used to earlier. So it's now n-2. So my degrees of freedom are 13. Again, using the table, so those of y'all that have a TI-83, you are going to need to see that table. For those of y'all that have a TI-84, you can use the calculator to help you out here. For those of y'all using your calculator to find this T value, again, remember this is what we call the critical value, and pretty much all critical values are found by starting in your home screen and hitting second bars, and then you're either going to do number 3 or 4. Now for us, because we're only dealing with T's here, we're going to say number 4, and then we're going to say 1 minus my alpha, which my alpha in this case was 0.05, and then I'm dividing by 2 because again it was a two-tailed test. If this was a one-tailed test, please understand that I would not actually divide by 2 here. And again, putting my degrees of freedom in, which my degrees of freedom on this one was 13. And then we're going to paste it in. Again, my TI-83ers, you do not have this option, so be aware. And this is where you get that 2.160. Again, same thing as if you look at the T distribution table. So if my T value that I got out was actually bigger, the test statistic T, if it is greater than or equal to this critical value, we will say that we're going to reject. Now, remind yourself that we just did all the math and got our absolute value of T to be 2.612, and that is actually bigger or equal to 2.160, which is, again, the critical value we just found. So the test statistic does fall in what we call the reject region, and since it falls in the reject region, we have enough evidence here to reject the null hypothesis, meaning therefore there is sufficient evidence at a 0.05 level of significance to support the claim that there was actually a significant level of linear relationship between the number of parking tickets a student receives during the semester and his or her GPA in the same semester. Again, it's only at a 5% level of significance, so again, I would probably want to do even more research to expand on that a bit more. Let's try another one. Now, an online retailer wants to research the effectiveness of its mail-out catalogs. Now, the company collects data from its 8 largest markets with respect to the number of catalogs. Now, these are in thousands, so be aware of that were mailed out one physical year versus the sale, which again is also in thousands of dollars for that year. The results are as follows. So again, I have this beautiful category item here. And again, take a good look. The first thing you want to do is we are going to do a hypothesis test to determine if there is a linear relationship between the number of catalogs that are mailed out to the sales. And again, we're going to do a level of significance here is going to be a 0.01. So since we're using a hypothesis test here, the first thing we want to do is we always want to state our null and alternative hypothesis. Now, we are basically asking whether or not it has a linear relationship. Again, I'm not saying whether it is a positive or a negative relationship. I just want to know, is there a relationship? Okay, which means that my null and alternative hypothesis are as thus. So my null is going to be that that Pearson coefficient equals zeros, meaning that there's no relationship. Okay, and we're going to say that our Pearson coefficient equals something besides 0. Again, determine what type of testing, and again, we're going to be using a t-level to testing here, and our level of significance was given to us, which was a 0.01. Now we're going to gather our data, and again, as we gather our data, the first thing we want to do is we want to calculate our correlation coefficient. Is it possible that to infer that the mailing a larger number of catalogs in a certain region influence the number of sales in that region? Because of this, what I'm going to do is I'm going to let X be the number of catalogs, and I'm going to let Y be the values of basically how much money we got back out in sales. Okay. Now, if you hit stat arrow over to calculate and number 4 lin reg, okay, and hit enter twice, that is actually going to give you what your calculator is going to give you for R. Now, again, if you're going to do this by hand, please note that, again, you're going to have to basically take that whole thing as is and follow your way through this formula. Now, remember, I did say there was another option of how to do this. So in order to get this test statistic that we've just gone all the way through for, again, I'm looking for the test statistic here. I always want to start with stat edit and put my items in here, but I do want to move over and hit stat arrow all the way over to test because we're running a hypothesis test here. And if you'll actually arrow all the way down to F, you'll notice that it says lin reg t test. And if I run that, I can say list 1, list 2, line up what was that alternative hypothesis. Yours it should, I think, automatically put in reg equa 1, which will be y1 there, and click calculate. Now, as you click that, what's really awesome and unique here is that we end up with a lot of information all at one time, and it does do an awful lot of stuff. Now, if you hit R, scroll down all the way down, you will eventually see that R that we got, which is the same R that you have here, which is your correlation coefficient. But notice one of the very first things that it spit back out was that t-value, which again is what the whole formula is looking to try to figure out. And again, we talked about this when we were doing hypothesis testing in chapter 10, is that we have what we call that test statistic, and then we also have the probability. Now we'll get to the probability later, but I do want to make sure that you understood that there was another option to do the test statistic besides this really scary looking formula here. Okay, so now that we've got our nice lovely items, we've got our test statistic, we do need to draw our conclusion. Now the one thing my calculator does not tell me is that reject region zone, which comes from my critical value. And again, the critical value, you're going to either use your t-distribution table with your degrees of freedom being 6, or you're going to use the calculator to get that critical value, which will be that 1 minus alpha over 2 in the inverse t option with your degrees of freedom there. Okay, and again, basically we need to know this item because again, this t alpha over 2, and again it's divided by 2 because it's a two-tailed test here. This t value, this critical t value here, is basically where I'm getting off for my reject zone. As long as my absolute value of that t is greater than or equal to this number here, we're in the reject zone and we'll reject the null in favor of the alternative. Now in our case here, our test statistic as we did it was 1.431, and that's actually smaller or less than my t alpha over 2. So in this case here, we would say we fail to reject the null hypothesis, meaning there's not enough evidence at a 0.01, or also known as 1% level of significance, to support the claim that there was a significant linear relationship between the number of catalogs distributed in a particular area and the corresponding sales in that area. Now, many times we're actually tempted to say that because of the linear relationship between the two variables, it's statistically significant. A change in one variable must cause a change in the other. However, it's so much more complicated. The world is much more complicated than just a nice, lovely, this influenced that. So when we do a correlation between two variables that is statistically significant, one of at least 4 different things may actually be going on. And I do want to illustrate that as we follow here. So we might have basically our variable x kind of causes y, or it could be in reverse that the variable y causes x. It could also be that the variable x influences y, but they're also both influenced by some other variable of z. Or it could be that x doesn't actually cause anything to do with y, but both are influenced by z, which does have that kind of weird relationship with it. Okay? So when you are taking a look at this, suppose that there's this correlation between these two variables, x and y, and we're going to naturally assume that x causes y. However, if we reverse those variables, in reality, y may be causing x to change. And on the other hand, there might be some type of combinations of factors influencing our response and or explanatory variables there. With the x variable, it may indeed influence y, but there could be that random third variable we talked about, z, that could be influencing them both. So there's really an awful lot in this real world that could make this kind of very weird. So even though a correlation does exist between two variables, one is not influencing the other at all. We cannot say that a correlation is the cause of it. Okay. Now we do have what we call the correlation of determination, the coefficient, sorry, of determination. The coefficient of determination is just basically your correlation R squared. It's kind of like your standard deviation and variance, how they are related. The coefficient of determination is related to the correlation coefficient. Okay, now it is measured as a proportion of the variations, hence why it's got R squared variations, in the response variable of y that can be associated with the variations in the explanatory variables. So say you're looking at a correlation coefficient for the relationship between the number of rooms in a house and their prices, and you get an R equals 0.65. So how much of the variations in the house prices can actually be associated with the variations of the numbers of rooms in a house? Well, again, I basically started off by saying that the coefficient of determination will tell us the amount of variations in the response variable. Again, I said here that the correlation coefficient for the relationship between numbers of rooms in the house to their price is this. So the correlation of determination tells us the variations, meaning that the house prices that is associated with the variations of rooms. Okay, kind of like a reverse order of what we just said. So instead of rooms to the price, it's going to be prices to the rooms. Now, the correlation of determination for the relationship between the number of rooms in a house and their prices will tell us the proportion or that percentage of variations in the housing prices. And this can be the association with the variations of the number of rooms in that houses. Again, it is basically the coefficient of determination. That is what it's called, and it's equal to the square of the correlation coefficient. So basically just take R and square it. So they gave us R equals 0.65. So I'm going to take that and square it, and I'm going to get a 0.4225. And again, remind yourself that that is, if you look at that in a percentage form, 42.3% of variations in the housing prices can actually be associated with the variations of the numbers of rooms in the houses itself.